Okay, let's dive right into this explainer. Today, we're going to do a complete mindset shift. We really need to stop treating printed circuit board, or PCB fabrication, as this simple, late-stage checkout process. Instead, we have to start treating it as exactly what it is, a high-stakes engineering decision. You know, you've probably spent weeks, maybe even months, perfecting a digital layout, but getting that design out of your software and into the physical world, that requires a completely different level of scrutiny.
Because here is the harsh reality of hardware development. Choosing the wrong PCB manufacturer can absolutely turn a perfect design into a complete failure. Before you even think about placing that order, we need to talk about the severe consequences of manufacturing misalignment. When your digital design constraints don't match the actual physical capabilities of your fabrication partner, that mismatch translates instantly into wasted time, burned budgets, and delayed product launches, and nobody wants that.
So to make sure that doesn't happen to you, we're going to systematically run through a 5-point high-stakes checklist today. We'll cover the manufacturing stakes, design rules and validation, physical layers and precision, avoiding common assumptions, and finally, integrated engineering workflows.
All right, let's jump right into part 1, the PCB manufacturing stakes, and why we need to prioritize precision engineering over simple production.
The absolutely crucial point here is that PCB manufacturing is not just mass production, it is precision engineering. Think about it. A microscale error in your trace width, a tiny via size discrepancy, or just an incorrect material selection, that doesn't just cause a minor glitch, it cascades into a macro-scale system crash. Literally, if a trace is etched even a fraction of a millimeter thin compared to what you designed, the current density might exceed its physical limits and your board could quite literally burn out.
Which brings us to Section 2, Design Rules and Validation, or how we establish a rock-solid digital foundation.
This leads to the very first question you must ask any potential partner. What specific design rules do you actually support? This sets up a rhythmic checklist you absolutely have to follow before you hit that submit button. You just cannot assume their physical machines can build what your digital software can draw.
Because here's the thing. Every single manufacturer out there has hard physical limits for clearance, trace width, and via size. Understanding these specific constraints up front is vital. For example, if you design a board with a 3 mil clearance, but your manufacturer can only reliably produce a 5 mil clearance, well, your board is dead on arrival. Knowing the rules is really only half the battle. Enforcing them is what prevents those mandatory, incredibly painful redesigns later on.
So moving on to question number 2 for your vetting checklist. Do you support Design Rule Check or DRC validation? You must actively interrogate their digital validation capabilities. It is definitely not enough for them to just take your file, say thanks, and blindly load it into their machines.
This validation process is honestly what separates a mere vendor from a true partner. A professional manufacturer actively verifies your design and runs their own internal DRC check against their specific factory floor tolerances. Their software knows the exact physical limits of their chemical etching baths and their laser drills, which allows them to catch the real-world errors that your software might have just cruised right past.
Let's transition into Section 3, physical layers and precision. This is where your design actually gets built.
So question 3 you've got to ask, can you produce multi-layer PCBs? Modern systems are highly complex and usually pretty space-constrained. You simply cannot assume all fabrication houses are created equal when it comes to navigating the Z-axis of your board.
As we step up from your standard, simple 2-layer setups to advanced 4 to 8-layer boards, the physical demands just skyrocket. When you are sandwiching multiple layers of copper and dielectric material together, you require incredibly precise stack-up control. If their lamination process is even a hair off, your impedance accuracy goes right out the window, and your high-speed signals will reflect, degrade, and ultimately fail.
Next on the checklist is question 4. What is your drill and via quality? We need to look at how they handle the literal holes in your design, because these are the arteries connecting the different layers of your board.
Drill precision fundamentally affects your board's reliability. We're talking minimum drill size, plating quality, and overall via durability. If their drill bits wander even slightly, or if the copper plating inside that microscopic hole is too thin, the via will physically break under normal thermal expansion. And those small errors, they cause intermittent signal failures, which is for sure the absolute worst kind of bug to troubleshoot. It can literally take weeks.
All right, Section 4, avoiding common assumptions. Let's look at the human element in manufacturing.
To stop those bad assumptions in their tracks, the fifth critical question you have to ask is, what materials do you use? The physical substrate of the board itself is an active component of your circuit. It's not just a blank canvas. You've got your standard options like FR4, and then specialized options like high-frequency laminates. And this choice directly dictates heat management, signal loss, and durability. Like, if you're designing a high-speed RF device and you just assume standard FR4 is going to work fine, your signals are going to attenuate so heavily they might not even reach the antenna. And here's a pretty fascinating truth. Most engineers don't actually fail in their design capabilities. They fail in their manufacturing assumptions. Inside the software, everything looks flawless, right? It works perfectly in theory. But on the factory floor, reality hits. Ignoring manufacturer limits, using the wrong clearance rules, or dictating completely unrealistic via sizes will ruin a theoretically perfect design. Bridging this gap between digital and physical is the real secret to a successful build.
Finally, let's wrap up with Section 5. Integrated engineering workflows, and how we actually bridge that gap.
The good news is, you don't have to navigate all this alone. Modern engineering teams are bridging the gap between design and physical fabrication by relying on integrated workflows. Platforms like NeuroCircuit actually align your PCB design with real-world fabrication right from the very beginning. By baking the actual factory floor constraints directly into your design environment, you drastically reduce errors before production ever even starts.
So let's recap with this thought. Choosing a PCB manufacturer is not a simple purchase decision. It is an engineering decision that defines the success of your product. You have to validate the rules, check the DRC process, verify multi-layer capabilities, investigate their drill quality, and confirm the materials. The next time you route your final trace and get ready to export those files, I want you to ask yourself, are you just throwing your design over the wall to a vendor, or are you collaborating with a true engineering partner?